Okay, let's try again. So for the sake of having this recorded, I'll start back. So we're going to cover anchored walls today. We covered cantilevered walls last time. The failure modes for anchored walls are different than they are for cantilevered walls, so we'll need to describe those failure modes. And then the assumptions we use to analyze them. This problem is statically indeterminate, unlike the cantilevered walls, and so we'll have to make some assumptions about how to solve it. And then you'll have to obviously be able to compute the earth pressures, and there are 3 different cases where and the earth pressure diagrams are different for each of them, just as they were for cantilevered walls. In a case where you have sand in the backfill and sand in the base, in a case where you have sand in the backfill but clay in the base, and in a case where you have clay in both of them. And then when we compute the moments for these, since we're using assumptions for a statically indeterminate solution, we're going to find that the moments we compute aren't correct. But we're going to use 2 methods to do that, the free earth method and the fixed earth method. You need to know how to do those. And then we're going to use an empirical method called Rowe's moment reduction method to actually get better estimates of the moments, and we'll discuss how we do that. So what we're not going to be doing is doing finite element calculations of this, which is the solution that you need to do if you want to get the moments computed correctly without using the Rowe reduction factor. So let's talk about these basically. So there's the anchored walls. The difference between an anchored wall and a cantilevered wall is this would be our wall in place here. Here's the mud line. Here's the soil line above. And instead of just being cantilevered in here, we have some system back here which is providing a horizontal force to stabilize the wall. We'll talk about there are 2 ways to provide the anchoring system. One is that you just have a concrete dead man back here, which can be just a concrete block. In plan view, if this was our sheet pile wall, we can just have a tie rod every so often and have a dead man in. Or sometimes they'll actually put a continuous wall back here to tie them into if the anchors get close together. And another common way, instead of having a concrete dead man, is you just drive a very short wall back here. So this is actually, in this case, there's a cantilevered wall on both sides. Sorry. In this case, there's a sheet pile wall in the front, and in the back, there's a little sheet pile wall. It can either be in segments tied back to each anchor, or if the anchors get close together, you can drive a continuous sheet pile wall. But this one can be much shorter than the front one, because it's not retaining any earth. It's just providing enough resistance to provide the anchoring forces you need. It's also possible to actually just have an anchor tied down here, but this is not very common in sheet pile walls. We're not going to cover that method of anchoring. We are going to cover that method of providing tie-back support when we talk about braced excavations, and the procedures that we use in there you could use for a sheet pile wall. So we're going to cover that when we talk about braced excavations and excavation support. So the failure modes. Well, the first mode that we have to worry about, particularly if we're in a condition where we have clays in the base, is basal stability or global stability. And we're actually going to, we actually have a shorthand way for calculating this. This is, again, sort of a bearing capacity or slope stability problem. But we're going to call this base stability also. And this is one case where we're actually going to check a global stability method, and there's a way to do it with sheet pile walls. The other problem you can have is that you have insufficient anchorage in the toe, and the toe actually then kicks out due to insufficient passive resistance beneath the toe. So you've got your whole anchor system designed, it's holding up fine, you got plenty of forces to anchor, but the toe kicks out because you have insufficient penetration into the foundation soil. And the failure on the other end of the wall you can have is where you haven't properly designed your anchor, and your anchor actually fails and moves, and then you're actually going to have the top of the wall move out. So you can have sufficient anchorage down here, but if you've designed your anchoring system incorrectly, then you can get a failure in your anchoring system. That's another passive failure, a passive earth pressure failure. But then your anchor can pull out. And then there's several structural failures you can have. You can have your tie rod fail in tension. You can have a failure between your tie rod and the system that you use to connect it to the sheet pile. We're not going to cover the details of any of the connections, but that typically this connection is what's called a whale or a whaler. And it's essentially a horizontal beam that connects the tie rod system to the sheet pile. So your sheet pile comes down like this, and then you have, lots of times it's two C channels put back to back, and your tie rod comes between those and goes back. And then these two C channels run the entire length of the wall. So if I was going to look at the wall from this point of view, what I would see, I'd see the sheet pile wall along here. Then I'm basically going to have a beam that runs across in this direction, and my tie rod will be attached to that beam at several locations. And that beam can either consist of two C-sections that are welded back to back with enough space for the tie rod, or you can actually just have a beam with penetrations through the beam. But the C-sections are very common. So this thing is called a whale. I don't know why it's called a whale. Called a whale or a whaler, but it's essentially a horizontal beam that you're using to transfer the concentrated loads from your tie back system to spread them across the wall. And then the other thing we can obviously have is then a failure in the moment capacity of the sheet pile wall itself, similar as we did in the cantilevered walls. All right, so let's talk about basal stability first. So basal stability is generally a problem when we have clays. When we have sands, that's generally not a problem. It's generally a problem when we have clays. So here's and again, we're doing this in the most typical application for sheet pile walls, where you're doing this in a marine environment. You've got water on both sides of the wall. So again, in the upper part of the wall, we just have gamma H prime. Gamma prime times H is the vertical stress that's applied here. And if we have a cohesionless soil and we're doing this for phi equals 0 conditions, then remember the passive and the active earth pressure are the same on each side. We have the passive and the active earth pressure are the same. They cancel the Ka gamma times, I call this Z2. Gamma 2 Z2 is going to be, the slope of this is going to be the same as the slope of that. And the only forces I have on the wall are 4SU, because remember I've got negative 2SU on one side and positive 2SU on the other side, so I have negative 4SU, and then gamma H times, gamma prime times H, because that's just transferred directly into horizontal stress here, because this is just a surcharge load, right? That's a surcharge load, and you have the surcharge, which is gamma prime H times Ka, which is equal to 1. So the net capacity on the passive side of the wall is 4SU minus gamma prime H. That makes sense? Do you know where the 4SU comes from? Yes, no? Okay? So this is my net diagram. So that's my net passive resistive is 4SU minus gamma prime times H. And we're going to introduce a concept here called the stability number. This concept is used in slopes and retaining walls, a lot of different things. But we're going to define the stability number S sub n as our undrained shear strength divided by gamma H. So if we substitute in 4SU there, then we can easily see that when the stability number is equal to 1/4, we essentially have a factor of safety of 1 against failure. Now, this model is a simplification in that we have adhesion between the wall and the soil. So we'll define a new stability number S prime that includes that fact. And we're just going to take the stability number S and multiply it times the square root of 1 plus whatever our adhesion is divided by our undrained shear strength. And we talked about how to estimate the adhesion last time. Well, typically, for typical values of the ratio of the adhesion to the undrained shear strength, this number is going to come out to be around 1 1/4. That is the square root of 1 over, excuse me, the square root of 1 times CA over SU. So we just plug that in our equation, so that means that S prime of n is just going to be SU over gamma H times 1.25. And if I then do my substitution here again with 4SU in here, it tells me that this should be a prime right here, excuse me. That S prime n is going to be 1/4 of 1.25, or about 0.31, and that's going to correspond to a factor of safety of 1. So these should both be S primes. So when we check our stability, what we want to do is, when we're checking basal stability, we just want to make sure that S prime is greater than about 0.31 times whatever our factor of safety is that we're happy with. So if it's a factor of safety of 1.5, if it's a really sensitive structure, you might want to do more than that. But we're just going to make sure that the stability number. So this is our check on global stability. This is preventing our global stability, or what we call basal stability. Now, this only applies to if phi equals 0 conditions, but that's the most common time you're going to have a basal failure, when you have a soft clay. So that's our base check. So once we've done the base check, this is the design approach. We're going to use, the problem is really a soil structure interaction problem, and it's an indeterminate structure. We really need to know the stiffness of the soil and the displacement of the soil to calculate the problem, because we've got more unknowns than we have equations to solve without including stiffness. So the wall loads are dependent on the stiffness of both the soil and the wall. It's an indeterminate system, as we just said. So in order to get a complete solution to this, we're going to have to use, just like any indeterminate system, we're going to have to use load displacement mechanisms, or we're going to have to know the stress strain properties of both the soil and the wall. So that means we're going to have to run a finite element program with nonlinear soil models, which we can do. But there are several simplified approaches that we can take to do this, and that's what we're going to go over today. So these are both based on theory and empiricism. They're very common design techniques that are used and have proven through time to be satisfactory. And we're going to be using those today. But the one thing they don't allow you to do is to estimate displacement of the wall, because they explicitly don't include that relationship between the stress-strain relationship of the soil. So if you need to estimate displacements, then you do need to go back and run a finite element solution with a nonlinear soil model. All right, so let's talk about, to understand the problem, let's talk about what happens to the loads on the wall as we increase the embedment. So if we have a very shallow embedment for the wall, we're going to get active pressures on the back of the wall, and then we'll have a very small net passive pressure on the front. The wall's actually going to move out, and at the base of the wall there will be some deflection, because the wall will actually be curved. We can't have any moment at the base, but there'll still be some deflection, some angular deflection, I guess, rotation. If we increase the depth of penetration, we'll eventually get to the point where the base of this is fixed. In other words, there's no displacement there, but there'll still be a curvature of the wall. There'll be a rotational movement there, but there won't be any lateral displacement. And then if I go as I go deeper, what we're essentially doing is decreasing the deflection in the wall down here. So this alpha term here, the angle of this will actually decrease. And if I get it to the point where that flips back the other direction, I'll actually start to develop some net passive resistance on the backside of the wall as we get with cantilevered walls. And then eventually, if I go deep enough, I'll get to the point where I have a fixed point back here. There's no deflection there. There's no deflection at all back here, and I'm going to develop the full passive pressure on the backside. So as you can see, the actual solution of the problem is going to depend on how much embedment I have. So let's first talk about. So this is just a conceptual sketch to show you what's happening to the earth pressures as you increase the depth of embedment. So let's look at the free earth method first. So in the free earth method, we're assuming that the displacement of the wall is a rigid lateral displacement and rotation about the top of the wall. And in that case, the loads in the wall, we have the anchor force. We're going to assume that we have active earth pressures on the backside of the wall, and that we develop passive earth pressures on the front side of the wall below the depth of embedment. So we end up with a net earth pressure diagram that looks something like this, which corresponds, if you look at it, corresponds to this condition. The shear in the wall will then look something like this. And the moments in the wall will look something like this. And obviously the maximum moment will occur where the shear is equal to 0. We'll also have a local maximum moment here, but this one will always be greater. So the moment at the tie location is not going to be the maximum moment in the, it's a local maxima, but it's not going to be the maximum moment in the pile. It's going to be this one down here. So let's look at this diagram a little more carefully. So generally, the easiest way to divide this up is to, we generally are going to assume that we have one soil above the base and a foundation soil below. And so up here, we're going to call this gamma prime here. We're going to call it gamma prime 1. And we'll have phi1, and we'll have both Ka and Kp1. So the slope of this line will be 1 here, and then this will be Ka. This is for a sand over a sand. I'm not sure I said that. Then the slope of this line is Ka gamma 1 prime times Z1, and we're assuming the groundwater table's at the surface because it's convenient. And then, as we showed, similar to the cantilevered wall, then the slope of this line is going to be Kp2 plus Ka2 times, because remember, you got the active pressure. You're going to have on this side of the wall, you're going to have Ka times gamma prime 2 Z2. And on this side of the wall, we're going to have Kp times gamma prime Z2. So you're going to have the net sum of those. And I'm trying to remember if this is right or if that's negative. I can't remember right now. I'm not sure. Seems like that should be negative. I believe that should be a minus sign. So we can write the equations for this. And so we'll just call HT the height where the tendon is, where the T force acts. H is our total height of the wall. And then it's convenient to some moments about T because we don't know T. So that's a convenient place to some moments. So if we do that, so P1 is going to be our earth pressure force from the active pressure above, and the moment arm for that one is going to be HT minus H over 3. So that, and then P2 is going to be this little triangle here. Well, P2 is going to be HT, the force of that we can compute from the earth pressures. We'll do those down here in a second, but and the moment arm is going to be HT plus Z0 over 3. And Z0 is this point where the force curve, if you want to think of it, it's not the shear, it's not the shear, but it's the earth pressure force intersects 0. It's not the shear diagram because it's leaving T out of the equation. And then minus P3, and the moment arm for P3 is going to be HT plus Z0 plus 2 times D0 over 3, where D0 is the depth of below this point of 0 earth pressure. So D is our total embedment. Z0 is the depth where we find 0 net earth pressure, and D0 is the depth below that. And we can calculate each of these forces. So P1 is simply 1/2 gamma H gamma squared gamma EQ times Ka, and where gamma EQ is the weighted average of gamma above the mud line. Generally, it's convenient if you have different soil layers back here. It's convenient just to calculate an average gamma and plot it that way because it's just a lot easier to solve the problem. So P2 is just going to be Z0 times H. Oops, that's it. No, Z0 times H times gamma equivalent for the base times Ka2. And then P3 is just going to be 1/2 gamma 2 prime, which is going to be the gamma from the base, times D0 squared times Kp2 minus Ka2. So we can solve for, from this, we can solve for Z0, for D0, and then we can just compute T as from summation of forces in a horizontal direction equal to 0. So that's for the case where you have a sand over sand layer. So for design, what we do then is we increase the depth by, again, 20 to 40% to account for a factor of safety. Or we can factor Kp by 1.5 to 2 when we do the analysis, and we'll just get a deeper depth. We discussed this last time. Then we're going to find the maximum moment in the pile, and we'll find out. We'll draw our shear and moment diagram, and wherever the maximum moment is, wherever the shear is 0 is our maximum moment. This moment is going to be significantly larger than the actual moment in the pile, because if you go back, what we've done is take a statically indeterminate problem, make it statically determined by our assumptions. If you go back here to this original assumption that we get this kind of displacement, see, this is rigid. We're assuming that we have a rigid, and the simplest way to think about this is we're assuming we have rigid motion in the pile. So if we have rigid motion in the pile, it's obviously going to take a lot of moment capacity to keep it rigid. It's actually not going to be rigid. It's actually going to flex. So the moments in it are going to be substantially lower than what we calculate with this. But this is a real simple method because it's a statically determined problem based on the assumptions we made. But if you design your if you select a pile based on this, you're going to be putting a really bigger section. You're going to require a much bigger section modulus. You're going to compute a much bigger section modulus than what you need, and you're going to be buying a whole lot more steel than you need. And that's generally a good way not to win the bid, is to buy too much steel. So we need a method. To reduce the computed moment for this, and we'll use a method that's called Rho's moment reduction method. It's a very old method, but it's a very simple method. And it's just an empirical way to reduce the required moment in the pile to get back to one that's reasonable. So we're taking a statically determinate solution, assuming the pile just rotates and kicks out at the toe. We're not accounting for any flexure in the pile or any inflection points in the pile. And so we're going to get much higher moments. So how do we apply Rho's reduction factors? Well, there's two different methods, one for sand and one for clays. And this one came out of the 99 FHWA manual. I believe it's also in both the Corps of Engineers manual and the USS Steel manual. But the moment reduction is based on a parameter they call Rho, because I guess the guy who developed this, his name was Rho, so that was clever. So in sands, Rho is simply equal to h plus d to the fourth over EI. So if you want to think about this, this is really accounting for the flexibility in the pile versus the stiffness of the soil. If you want to think of h plus d to the fourth, is having to do with how long the pile is compared to the stiffness of the pile. So this is a relative stiffness of the pile. These are dimensional parameters, so you need to be very, very careful to do this correct. If you do this, you've got to have h and d in feet and e in psi, and the moment of inertia is going to be in inches to the fourth per foot of wall width. And if you want to do it in SI, that's fine, but you got to have h and d in meters, e is in MPa, and I is in meters to the fourth per meter of wall. So when you look up, although you might think that inches to the fourth and meters to the fourth are kind of strange units, when you look at sheet pile walls, they're always tabulated in those because that's the way we do this. And then once you know Rho, you just come in with whatever your Rho factor is, and then there's a range of values here between loose sands on this side and dense sands on this side. If you have, and you want to stay, you basically want to stay in this region. If you're below this region, you're in an unsafe zone. If you're above this region, you're in a safe zone, but you could also interpret that to mean a overly conservative zone. And what you get out of that is the MD over M max. So this is your actual moment reduction factor. So if I come in here and I calculate that I've got a row of 3, and I'm in a dense sand, I could be using something here like a reduction factor of something that's like 0.55 or so. So you're just going to take the moment you calculated from the free earth method. You're going to use the length of embedment that you got out of the free earth method, whether that was by factoring the passive capacity and then just calculating a depth, or just calculating a depth with a full passive capacity and increasing it by 20 or 40%, whichever way you want to do it. You're just going to calculate the moment you get from that method and then decrease it by this amount based on the relative stiffness of the pile section. So it's an iterative solution, obviously, because you got to pick a pile section, and then once you know a pile section, you know Rho, and once you know Rho, you're going to reduce your moment, so then you get a different pile section. So it's a little iterative solution, but it doesn't take very long. If we're in clay, we're going to use the basal stability number to calculate our moment reduction. If you want to think about it, the basal stability number is really kind of a measure of how stiff the system is. As the basal stability number gets as the basal stability number gets small, then we're going to be close to failure, and we're going to have a much softer system. So in this case, the moment reductions are for basal stability number and Rho. So you notice here you have a different plot for different Rho values, and as a function of the stability number, and as alpha, and alpha is the ratio of H over D. So as you've got, if you think about it, as H over D gets larger, you're going to tend to have more movement of the pile. The system, as H over D gets larger, the system gets less stiff. the soil system gets less stiff. So, the free earth method. Let's just summarize that real quickly. We're going to use our assumptions for the free earth method are that we get rigid rotation of the pile about the surface. So we're going to get a full active earth pressures on the backside and full passive earth pressures on the front side. We're going to determine, and that turns it into a static problem, right? That makes it a static problem, a statically determinate problem. I'm sorry, they're all static problems. That's a determinant. It turns it into a determinate problem. We can calculate both our depth of embedment and the required anchorage force because it's now a statically determinate problem. We're going to increase D by 20 to 40%, or we're going to factor Kp going into it in the first place. That's how we're going to make sure that we have a appropriate system. We're then going to compute the maximum moment using that free earth pressure diagram. That's where it gets its name. It's assumed that we can fully mobilize passive and active on both sides. That number is going to be too big. We then reduce that using the Rose reduction factors. This is a little misleading. In order to use Rose reduction factors, you have to pick EI. So you're actually going to pick a pile. Based on judgment, you're going to take the maximum moment. You're going to take something less than that. Pick a pile. You're going to calculate the reduction factor, and it's going to give you a new moment. You're going to pick another pile, and you're going to go through a little iteration between this until you've got to the point where the moment and the moment you assumed is the moment you're getting out from the moment reduction method. Does that make sense? Because rho is a function of EI, right? Okay. So that's the free earth method. So what we're doing there is we're making our statically indeterminate problem a statically determinate problem by assuming we get rigid movement in the pile, and we're ignoring any soil structure interaction. So the fixed earth method is a more correct analysis, but it still has assumptions in it. But the fixed earth method, for the fixed earth method, the boundary conditions we're going to use is we're going to assume that we get this pile in deep enough. There's a point where the base of the pile is not subject to any displacement or any rotation. And so there's going to be an inflection point someplace in the pile if we get it that deep. This goes back to the assumption, this goes back to this earth pressure diagram here. We're assuming this one, we're going to get to this mode where the pile is deep enough that we're going to have no deflection at the base and no angle at the base. Alpha is going to be equal to 0. And in that case, since if alpha is going to be equal to 0 here and alpha is positive here, there's some place where there's going to have to be an inflection point. Okay, and for you structural engineers, what do we know about the inflection point? If this is a beam and we have an inflection point there, what do we know about the inflection point? We're getting a change in curvature, so that means that's a point of what? Anybody awake today? Your beam was smiling. It went from smiling to frowning, so what happened? 0 moment at the inflection point, right? Has to be. See, that wasn't so painful, was it? So I said this already. We're assuming there's no rotation about the base. There's rotation only about the anchor. So at the inflection point, we're going to have no moment at the inflection point. So our moments look something like this. So what we can do now is, if we knew where the inflection point is, we can now break this into 2 different beams where there's no moment at those, and solve them statically independently. We can solve them together to get the solution, because they're two two different beams if you want to think of it with no moment in the middle. But we have to know this point of inflection, Zi. So at that inflection point, there can't be any moment. So we break this thing into two equivalent beams, but we need to know where I is located. So that all worked. If we do the inflection point, then we can solve the problem because we basically have two equations and we can solve the unknowns. So our approximation of this one is we're going to approximate where that inflection point is. So Bloom developed an empirical relationship for, well, he developed a theoretical location for where the inflection point was based on the assumptions that we were using Rankine active earth pressure, and that the passive earth pressure was not 1 over Ka, but 2 over Ka, so it's less than you would do. And then we can calculate, so if from Bloom's assumptions, we know where I is, and then once we know where I is, we can solve for each beam through statics. So here's a procedure, and this one comes out of your FHWA manual. The procedure is also in the other design manuals I gave you. So first you're going to construct your earth pressure diagram. So at the top, this is going to be in the slope of Ka1, and at the base, the value at the base is going to be your gamma equivalent from your top times h times Ka1. And then this earth pressure diagram is going to start off at gamma equivalent times h, that's gamma equivalent from the surface, times Ka2, because your active earth pressure in the base could be different than your active earth pressure in the top. Right, remember we said before we were going to break our problem up into, right, we're going to assume that we have gamma 1 prime in the top and gamma 2 prime in the bottom, and Ka in the top and Ka in the bottom. Oops. So that starts there. It goes in the slope of Kp2 minus Ka. So this is correct, or that other arrow is wrong. And then at the base, I'm going to have some reaction here at point I. So this is the upper beam, right? I know that this is essentially a hinge where there's zero inflection. So I will have a reaction there because it's a hinge. I will have a reaction there, but there's no moment. Then Zi, this depth, we're going to compute from Bloom's relationship, which it's just going to give us Zi as a function of the friction angle of the soil. So that's our assumption. That's our approximation. We're assuming we know where this inflection point is. And now this is all known. We can solve for R and T just using statics because we know this depth Zi. We can compute the magnitudes of all the forces there. So that's pretty straightforward. But that doesn't tell us the required depth of embedment, right? That tells us the loads on this part of the wall. So now we need to figure out the required depth of embedment. So now we're just going to draw the free body diagram for the bottom beam. So the bottom beam, we now know R, and we know that the slope of this, right? The slope of that is going to be gamma prime times Kp2 minus Ka. So we know the slope of that, and then we just need to make sure that this area is enough to account for the to balance out R, and then we're going to find d prime from statics. So that's all we're going to do here. It's not going to be a completely static problem because we're actually going to have a moment theoretically in it, but we'll ignore that. And then we just increase d prime by 20 to 40%. And we go back and compute our maximum moment and select the pile. Now this one we don't use the moment reduction method because we're using that assumption that we know where the inflection point is it's going to give us a lower moment. So the procedures for these, I don't want to go through the procedures in details. They're laid out in I think all three of those manuals I gave you, in the FHWA manual and in the US Steel manual and also in the Corps of Engineers manual. But what's important to understand here is what assumptions we're doing. So there's a big difference between these two methods. In the free earth method, we're assuming that we have rigid rotation here, and that makes the problem statically determinate, but it gives us a really high moment because we're assuming I mean, if you want to think about it, we're almost assuming that the wall's infinitely stiff, so we're going to get a really high moment. And then we're going to use Rho's reduction factor. And there's one for sands, and there's one for clays, to reduce the moment when we pick the section modulus for a pile. We're going to design the depth of embedment, everything with the assumptions, with the free earth assumptions. We're going to use this earth pressure diagram. We're going to use this earth pressure diagram to compute our depth of embedment. But when we calculate the moment, we're going to reduce it because we know that the way we're doing this, it's too high. All right? That's the free earth method. In the fixed earth method, we're going to assume that we have the pile deep enough that at the base of the pile, there's no rotation and there's no displacement. And then we're going to use a theoretical solution for a simplified case to tell us where the inflection point is. Now we've got an additional equation because we know that the moments are equal to 0 there. And we can solve, and here's that approximation we're going to use to find Zi. And now we can solve, whoops, sorry. Once we know Zi, we can solve statically for the top equation. That'll give us the anchorage force, and it'll give us this reaction at the hinge point that we've assumed. We then take that reaction at the hinge point, and we know the slope of this line, and so we can calculate the embedment required to get the required reaction for that. And now we know the depth of embedment. We can draw our earth pressure diagram, compute our maximum moment, and select our pile. So we don't do the moment reduction in this method because that assumption about the depth of the inflection point is accounting for that soil structure interaction for us. So one of these is harder than the other, right? Okay. So that's how so now we've finished that design. And we know, let's see where I'm at here, hang on a second. Yeah, I think we'll press on, finish this, take a break, and then come back and look at our homework problem. So we know T, we know the anchor force we need now. So now we need to make sure that we have an anchor block that will provide that anchorage force for us, right? Well, one of the first things you want to do is, it would be really bad if you remember to save space in these early pictures, we showed the anchor block, quite close to the wall, and there's a real problem with this picture. If the anchor block was that close to the wall, what's our problem? Yeah, we compute the active zone back here, something like that. That anchor's not anchoring anything. It's just along for the ride, right? So the first thing you got to do is get the anchors far enough behind. You don't want it within the active zone of the wall. Otherwise, it's not anchoring anything. It's just the whole wall's going to go. The whole anchor wall's going to go with the wall. So the very first thing you need to do is to make sure that you get the anchor far enough back. So that's pretty easy to do. What you're going to do is you're going to draw a line that's 45 minus phi over 2, which is your active wedge. So that's what this is. And then you're going to have a passive wedge from your anchor block, and that's going to be 45 plus phi over 2. That's the interior angle there. And obviously you don't want those two to intersect. Well, if those two intersect, you shouldn't have a problem. And as these numbers become, if you move the block this way, then you're not going to suddenly have failure, but you're going to reduce the capacity of your block. So you don't have to have the block this far away, but if you don't have it that far away, you're going to actually have to have a bigger anchor system because you're going to lose some of your capacity. So that's the first thing you need to do. You need to make sure that these two, this passive wedge and this active wedge, preferably don't intersect each other at all. That's a pretty easy check to do. It's an iterative solution because the depth of this wall is going to depend on what anchorage force, but you start off with an assumption of what the depth of the anchor wall is going to be, and then compute this. It's pretty straightforward to do. And then the next thing we need to do is make sure that we actually get the capacity out of the dead man or the anchor wall we're using. So the earth pressures you've got acting on this, realize that behind the wall you've got an active wedge which is pushing on the wall, right? And in front of it you've got whatever your passive wedge here, and here we've quite appropriately shown that as a curved line because we know that we're not going to get a full triangular wedge out of there. We're going to get some kind of a wedge that's actually more of a log spiral wedge, which is why, by the way, this is conservative to put this is conservative to assume that this is your interaction because this failure surface is actually going to come out shorter than that. So you don't need to add a factor. If you've got this check here, you don't need to put a factor of safety on it because this passive wedge isn't going to go that far. It's going to curve up like this. Okay, so these are the forces acting on the wall. So in the case of sand, or if it's clay for the long term, where you've got C equals 0 conditions, then you just got passive pressure on the front side and active pressure on the back side. You got to find an H that gives you a net force that's satisfactory, and be sure to. This is the case where you want to really, really be sure to use a log spiral method because this is you're getting all your resistance from your anchor block or your dead man is coming from passive resistance. And you don't want to overestimate that. So this is a good time to be using log spiral curves. And using Rankine and underestimating it is probably not a good idea either because you're going to get a design that's overly conservative. So this is a good time to be using your log spiral method. For the short-term case for clays, remember that on the backside you're going to have a tension crack open that's a height of 2c over gamma. On the front side, you're going to have 2c, and you're going to have your active. The slope of these is both going to, Ka is going to be equal to Kp is going to be equal to 1. So the slope of these two is going to be the same, but you'll still have an imbalance in the earth pressure force. So you have to do this little calculation. So this is the same as the calculation you do for a cantilevered wall. And if you're doing an anchor wall that's continuous, so if this is your sheet pile wall and your anchor's back here, and if it's a continuous wall that goes on forever, then you can just do this calculation and you're going to get an answer in, you're going to get a H assuming that the wall is continuous on forever and ever. It's common, if you don't have to get your anchors too close together, to actually have finite-sized anchor blocks that placed along the back of the wall instead of having a continuous wall. And if you do that, it's a 3D problem. And if you think about it, here's your dead man right here. And as he moves in this direction, you're going to get this passive wedge that you'd calculate from using a log spiral or whatever method you want. But you're actually going to have additional resistance because there's going to be shear along the sides of this, and you're actually going to fail a zone that's actually bigger than that. So you're actually going to get more resistance than you'd calculate just by using regular earth pressures. In addition, if this is a fairly large dead man, you're going to have friction on the base. So the FHWA manual shows you how to do this calculation, or the Corps of Engineers manual shows you how to do this calculation. And they're basically using empirical, they basically give you empirical factors to account for both the, well, account for the edge effects, and then you add the base friction. So let me correct that. So they have some empirical ways to account for the edge effects, and the base friction you just simply calculate as tan phi times the weight of the material acting on the base. And if you're going to use finite-sized anchors, you should do this calculation because it's going to make a significant difference. It's going to significantly increase your capacity. Remember, by the way, when you're calculating T, when you get T from this answer, right, this is going to, the T is going to be in terms of force per unit length, right? Because we're doing a calculation for an infinitely long wall here. Everything's per unit length. So once you have T there, when you go to translate that to, if you're going to use finite size anchors, if you're going to use individual anchors, you're going to have to know your tributary area from your wall. So if your wall's like this, you know, if you've got an anchor here and an anchor here and an anchor here, you know, the tributary area for this anchor is going to be halfway in between. And if you're going to put that back to a single solid dead man, make sure that you've actually got the total load from that area. You're not using some load per foot, and try and use some load per foot back here for your anchor block, because it's no longer, once you've decided you're going to use that single anchor and take it back to a single block, it's no longer a load per foot. It's actually a total load from that tributary area. If you're doing a continuous anchor wall, like we did in the previous one, if this wall is continuous, if the anchor wall is continuous, and you've got a tie back there and a tie back here and a tie back here, and they'll go back to the wall, then you can do this whole calculation in terms of the anchor, the anchor force from the wall in load per foot, load per length, and because your T's in load per length, and that's fine, and you can put the tiebacks in any place you want. And then you only need to do the tributary area to calculate the total load in the anchor to size the anchor itself. But when you're doing the earth pressure calculation, you can just do it in terms of capacity per unit length. But in this one, you can't, this is not a capacity per unit length problem anymore, it's a total capacity problem. Do you understand the difference between what I'm saying there or not? Yes, no? Okay. Cool, and I think that's all I've got. So I don't go through all the design details because they're spelled out quite clearly in all your manuals. All right? Let's take 10 minutes and we'll spend at least half hour starting on the design problem and at least calculate the earth pressure diagrams that you need, so you at least get a start on it, and you got some, and you're confident you know where you're going, and then we'll take off after that. Okay? All right.